All right, well, hello everyone, and my name is James Mastandrea, and along with Kristen Jaburek, we lead the LSIC Modular Open Systems Approach Working Group, and I'm really excited for today's panel. The Mosa Working Group is focused on ensuring lunar interoperability to make sure that we have a robust and sustainable lunar presence on the moon. We are leveraging the Mosa framework because we think it has many applicable aspects that can be used for lunar interoperability. Sorry, first time. So Lunar Interoperability today, and we will learn a bit about what Mosa is and hear from our panelists on how we should proceed with ensuring lunar interoperability. To give a bit of context, the Mosa Working Group was born out of the Surface Power Focus Group and quickly turned into an LSIC-wide effort as discussions on standards, modularity, architectures, maintenance, and repairability have continually been brought up in all of the focus group discussions, so we thought it'd be best to stand up this working group. And we also have point of contacts in each of the 6 focus groups who we're working with, along with the whole entire LSIC community. The goals of the Mosa Working Group have been to understand what technologies could benefit from standards, modularity, and open architectures, compile existing interoperability efforts. We don't want to reinvent the wheel here, so we want to understand what's out there, and to really identify critical interfaces that would benefit from standardization. And an example product of this working group so far that with help with the whole LSIC community is that now on Confluence, there's an extensive list of standards and interoperability efforts that we can pull from that hosts as a central library. Another goal of ours is to host community discussions, and as part of that, we've actually stood up a monthly working group meeting, and is the reason why we are here today to hear from our wonderful panelists. So, Jessy Schingler from the Open Lunar Foundation and I will be moderating today's panel discussion, and we will hear from Mark Mazzara, Robotics Interoperability Engineer and Project Manager at the U.S. Army, Meera Towler, Senior Research Engineer at the Southwest Research Institute, Matt DeMinico, Power Portfolio Manager at NASA Glenn Research Center, Amalaye Oyake, the Senior Flight Software Engineer at Blue Origin, and Chad Thrasher, Systems Interoperability Lead at NASA's Artemis Campaign Development Division. To make sure that we get through several important topics, we've created a list of questions, and we've pulled those questions, or we've captured questions that continually come up in most of the discussions throughout the various focus groups. However, I still encourage everyone to submit questions through Slido, because what we'll do is we'll summarize those questions, put them on Confluence, address those questions, and then also tomorrow, here's a quick plug for one of the breakout rooms. There's a space law, Mosa, and the big picture breakout rooms. We're going to use these questions to start some of the discussions tomorrow. So without further ado, I'm now going to pass the floor to Mark Mazzara for a brief introduction to Mosa. And as a reminder to all of our panelists, I will give you a 1-minute warning. So Mark, take it away.
Okay, thank you very much. Can you hear me okay?
Yes.
Okay, good, thanks. If we can go to my second slide. So I work in, I should have spelled it out, but project manager for force projection in the Army. So I'm kind of outside this community's focus areas, but this is really exciting for me to hear everything you're working on. So I'll try to keep this, I'll speed through my slides, but basically we work on ground robotics as well as some other systems, and I'm going to talk about the modularity efforts that we have. I should mention the types of robots that we work on are primarily teleoperated over about 1 to 2 kilometers with streaming video and things like that. And I didn't put it on here, but my office actually works on a lot of other things that may be of interest to the NASA community, such as excavators, construction equipment, water purification, and some other things. If we could go to the next slide, please. Modularity. So I'm going to talk about kind of something we've done over the last couple of years to implement modularity, but really it's driven by our systems not being interoperable between the controllers that the operators use and the robots themselves and the payloads that we put on them and the radios that we put on them. And then we anticipate the payloads and sensors and software and the computing devices to evolve much faster than the mobility platforms that they're going on. Next slide, please. So just kind of a brief intro to Mosa, modular open systems approach or architecture, depending on who you're talking to. I think most people are probably familiar with this, but really it's all about separating the subsystems that are important to you from each other so that you get to a loosely coupled, highly cohesive functionality. And it's all about identifying those subsystems and specifying the interfaces between them as far as physical, electrical, logical, power, and in my mind, most critically, the software messages that are used between them. And there's a lot of benefits, obviously, the ability to upgrade things independently. We heard a lot of people in the last talk talking about using different payloads on reusable systems, and it gives you the ability to break some vendor lock and some other things. Next slide, please. So this is kind of a DoD definition here, Department of Defense, that is, but I imagine it's pretty applicable as far as the lunar community goes. But establish an operating environment as far as leadership making it a priority to do modular open systems, employ a modular design, like I said, identify the subsystems that are important and which ones you want to be maybe upgraded separately or repaired separately, or which things you envision the technology evolving most rapidly. We heard from the previous brief about a lunar mobility system being put out there for basically a 10-year life cycle. So it's interesting to think about what you may want to upgrade on that system within that time frame, if anything. I know it's hard getting things onto the moon, obviously, but you may want to upgrade one or two components on there if you want to do certain experiments on different fiscal years and things like that. Designate key interfaces. So like I said, you want to define the messages that are going to be interacting with any of those systems that are on board, and the power and the electrical, logical, etc. And then select and implement widely used consensus-based standards. So what I'll talk about on my next slide has to do with looking at different industries, forgetting those. And then certify conformance. You want to have methods for testing against your interfaces to make sure that the system works before you put it out there. Next slide, please. So this is kind of the crux of, so I used to work with Matt DeMinico when he worked for the Army. So I think that's how I ended up on this panel. But one of the things we've done over the last 10 years is we basically define the systems that we're interested for these ground robots as being basically the mobility platform, the robot, the payloads that go on them. So it's basically cameras, sensors, LiDAR, radios, different types of robotic actuators and things like that. And then the operator controller, and we basically standardize the interfaces between each of those subsystems. So we defined a thing called an interoperability profile, or an IOP, that tells you basically the two like industry standards that are most interesting to us are the JAWS, the Joint Architecture for Unmanned Systems, which I would suggest anybody working on robotic arms and autonomous payloads and things, you might want to look at that. I think probably have some applicability to space payloads. And then the CAN J1939, it's basically an automotive trucking standard. But we defined it down to not just the performance specification level, but to the product specification level, where it's basically level 3 TDP level of definition, And so for each of our programs that we buy, we basically put it in the contracts that you shall comply with the following interfaces, and anything you do inside of your blue boxes, we don't need to necessarily know about that. That's your own intellectual property, but just communicate to each subsystem using this set of messages. Next slide, please. So what that enables basically, and we've realized this on a few different systems that have been fielded over the last few years, is it allows us to separate our platforms from our controllers and from the payload. So we can configure different payloads on a common chassis for different types of users, whether you're Navy, Air Force, whether you're an explosive ordnance user, or maybe you're chem bio type of user, or maybe you're doing some kind of reconnaissance for a different mission. And then we can separate the controllers. All of the messages that are going over the air wirelessly are using the same message. So when we say we want a system to turn right, and that's what the robot receives, it doesn't matter if the input that they did that was through an audio voice mechanism, or a phone, or like a kind of Microsoft Connect kind of type of image recognition system, or a traditional like tablet. Next slide. And similarly, it enabled, so we also have basically autonomous trucks. So we have the ability to put some semi-autonomous mobility kits onto existing manned vehicles. So that basically what we do is we interface with their J1939 can that's already on their, say, John Deere vehicle or whatever. And then we talk to that kit using our IOP with basically a message set of J1939 messages. And then we talk to the, between the controller and the autonomy kit using a set of JAWS messages. And so we can kind of manage those systems separately. Next slide.
1 minute remaining.
Okay, 1 minute remaining. So specifying interfaces. I think I've really already covered all this. If you go to the next slide, slide 10. So I kind of looked at some of the systems that you all are working on. So landing and launch pads. I think these are good opportunities for standardization, power infrastructure, excavators, autonomous vehicles, water purification, etc. Review relevant standards. So you probably want to look at what can you reuse from other industries. And then also the nice thing about you guys doing lunar missions is you can do a greenfield approach where you don't necessarily have to start from standing on the shoulders of giants. You have a whole blank slate so that you can basically design modularity from the ground up. And then finally, my last slide here, which is taken from the Economist newspaper, but just slide 11. It's just, I'm sure you guys are much more familiar with this than I am, but look at all those subsystems. So you already have modularity designed into them. How well are the interfaces defined? I don't know if NASA defined those interfaces or if that was the purview of the vendor that designed this system, but that's definitely a good starting point for this system. And then I will turn it over to the next speaker and the rest of the panel. Thank you.
Thank you very much, Mark.
Well, thanks, Mark. I think we're going to have each of the speakers now go and sort of give a short introduction to yourselves and your work. And I believe we have 4 minutes per person, right?
Yep.
And we'll be keeping time to make sure that we're on track. 4 minutes per person.
For each, yeah.
Yeah. So maybe we'll start on the far right here.
So Matt's slides are up. Sorry, we're just going to start with Matt now.
Oh, I'm sorry. Okay.
Matt, take it away.
Great. Go for it, Matt.
All right, well, I just want to thank everyone, LSIC for having me here. If we go to the next slide, again, I'm at DeMinico, NASA Glenn Research Center, as Mark brought up. I had spent just shy of 20 years working for the Army in robotics, And actually, I think this slide will help kind of summarize why it's critical that we learn from PM Force Projection, DoD, and Mark and the groups that he's worked with, because as NASA and spaceflight, we don't really realize what they've done to kind of pave the way in this community. If you look if you remember early Iraq and Afghanistan, where IEDs blowing things, I mean, they needed robots out there, stat, right? It needed to happen immediately, and the rapid response, there was no Mosa used, and what they learned from that is most of the assets got divested. So Mark and the team, the R&D industry, PM, working with industry, so they came up with a new approach. And Robotics IOP, he mentioned that. Ross M was another one, one of the programs that I managed there. Picture it kind of like an app store-like system for robotic software. Really interesting system. And now those are actually widely adopted. So Mark mentioned some of the benefits: incremental upgrades, reduces cost, less spares, teaming, interoperability, allows non-traditional vendors in there. So we'll go to the next slide really quick. So how does that relate to spaceflight? Really, so if we're looking at boots on ground by 2025, I'm not suggesting, I don't think anyone is suggesting that we push a modular open systems approach on that aspect, right? That's emergency speed. But habitat, LTV, rovers, power, ISRU, those aren't emergency speed. And like Mark mentioned, we're starting with a blank slate. It's a great opportunity to start. So we can go to the next slide. I'm kind of the good idea fairy, so I take this big picture and say, where could we go with this, right? So if we look at this, there is absolutely no chance that we're going to send people to the moon solely to mine regolith, process it, store it, deliver. I mean, it's just not going to happen. But for the first time in history, in all of human history, we don't need to have people present to do this massive scale of work that we have to do here. So the technology's there, but only if we take the right approach. So if we can go to the next slide. This is, I think one of the people that was on the legal panel before, and the policy panel was saying, this is my thoughts. This is not necessarily reflective views of NASA. This is my thoughts on how we may approach this. So even though I work for NASA. So my thoughts on this is, let's do the basics first. So we look at power, we look at communications, maybe navigation. Those are very low-hanging fruit. It's very easy. We can get our feet wet with a modular open systems approach. A lot of the answers are already kind of there. We just need to formalize them and just go forth and do it. Learn to do it, working with the LSIC community and the international community. That's going to be absolutely critical. And then from there, then we take an approach of something like this massive robotics-enabled ISRU campaign, where we have all this modularity and we just develop and we build it up, right? So once we've learned the basics, we can do that. Looking at step 2, and the idea there is it's modular, it's upgradable, and it's affordable for commercial partners to design, build, and sustain, so that anybody can come in. You can have, I like to say, you have Billy Bob's Robotics Emporium. He's the world's best something, right? And their company is just world class, and they would have never thought to do anything in the lunar realm, but they're excellent in what they do. And if we have the right approach, we can integrate that into, effectively take non-traditional experts in the field and integrate them into our systems and bring them into the community. And then again, this step 3, so those architectures define the interfaces, and then everything can be independently developed, tested, and built. Time? That's it. Good.
Great, thank you. We're going to have Meera Towler from Southwest Research Institute. Go ahead.
Thank you. So I'm going to talk about a few places where we use Mosas in robotics work at SWRI. I'm going to start with a very concrete example, and then I'm going to move to one that's a little bit more unofficial, but is a really good example of one of the benefits of Mosas. And then I'll finally conclude by talking about where we can use this for the lunar surface. Next slide, please. So why Mosas? It avoids standards proliferation. A lot of us have probably seen that comic on the right from XKCD. Mosas also, because they specify interfaces, can help minimize the need for standards to stay very updated. So you don't have to necessarily wait for your standard to be updated before you can advance your technology. One thing that's maybe not necessarily true on this panel is the third one where it says soon. Waiting for standards to get updated can be a very long process. So if we can avoid that through using standardized interfaces instead, we can speed up our technology development. As has been mentioned a few times already, moving towards field swappable has significant advantages across all industries and very much so for the lunar surface. And also this enables more effective teaming to create the best possible system because as Matt just mentioned, you can pull pieces together to make your system. Next slide, please. So an example of a Mosa that we have worked on at SWRI is a project called Victory, but it didn't actually start there. It actually started back many years ago working on the 787. So we were the lead systems integrator for the network-based flight test for the 787. And then there was an effort through the DoD's INET program to apply that to a wider range of space or aircraft. So that's more generic for flight testing. And that eventually evolved into a project called Victory, which was a DARPA BRASS program, which focuses on interoperability initiatives. Victory is specifically a Mosa development effort that was aimed to streamline how to add critical systems to ground vehicles. Essentially, it was looking at how do you take all of these different systems that all have their own GPSs, 4 clocks, and combine them into only one. So can you communicate between these systems that are maybe made by different people, different companies, so that you can work a little more efficiently when you're adding on new components. The unofficial motto of Victory was adopt, adapt, author. So the goal was to adopt or adapt existing standards and existing systems as much as possible. Authoring was really a last resort, only if there was nothing out there that existed that would have worked for this application. Next slide. So an example of something that's not actually a Mosa, but it has some of the same benefits is ROS. And I think Alma's probably going to talk about that in a lot more detail later, but there's 2 ways that ROS kind of functions as a Mosa. Inorganically, the way ROS is written specifies how certain messages are defined, and so those messages will look the same across numbers of systems, pretty universally true. It's also organic in the way that the community has set certain standards. So if you want your code to work with someone else's code, you have to follow that same messaging procedure. So essentially what this does is that any camera in the ROS ecosystem that's running ROS should be able to talk fairly well to, say, a perception node running in ROS as well, because those messages are standardized. Next slide. So how Mosas can benefit robotics in space. The space industry, and specifically space robotics, is moving incredibly quickly. We need to be talking right now about how we're going to handle interoperability, but we maybe don't have the time for a full traditional standards development process. That might hold us up. But Mosas have enabled increased interoperability, which enables more collaboration, and therefore more rapid development in this really quickly evolving field. And then finally, field swappable components reduces launch costs and can enable increased capabilities with less hardware. And we have a great example from Wally on that one. Thank you very much.
Thank you. Now we have Amalaye Oyake. Sorry if I'm mispronouncing that. My apologies. Senior flight software engineer from Blue Origin. Go ahead.
Yeah, thank you very much for inviting me, and no need to apologize because my name is actually twice as long as what you see here, so no need there. But as you shared, I'm a senior flight software engineer at Blue Origin. Prior to Blue, I was at NASA JPL. I've been involved in standards activities for a very long time, and I have a few thoughts to share about modular open systems. So the idea of modular open systems is not new. These ideas have been around for a very long time. And what we are experiencing at this point is a lot of ambition and a lot of conceptual ideas for advanced technology in space. And so the phrase I'm going to share is this, that our capability has to scale to meet our ambition. And so if you look at NASA roadmaps and conceptual ideas and projects that are on the drawing board, you see extremely complicated systems, robotic systems and human-rated systems. One of the things that we have to think about is the type of technologies in terms of hardware and software that is going to operate and control these systems. So Dr. Gerard Holtzman, who was formerly at NASA JPL, produced a graph of the software lines of code for human-rated systems and robotic systems. And so for human-rated systems, as you looked out to 2020, you were looking at about 10 million lines of code. And for robotic systems, it was, I think, it was in the millions, but it was the human-rated software lines of code that was most alarming, because you saw this exponential growth over time. The challenge is the qualification of this software. Do you qualify this code using traditional means or manual means? And the answer is no, you cannot. So in my area, what I'm working on is a robotic framework for space robotics. It's called Space ROS. It's a collaboration between NASA, Blue Origin, and Open Robotics. And this is an example of a domain-specific software architecture. Domain-specific software architectures are not new. You have architectures for flight software like CFS, F prime, and now most recently what we're working on, Space ROS. So I was involved with the flight software workshop, and we provided a platform for CFS, and I was also the first user of the F prime software framework. So what I'm trying to share is that
1 minute.
yes. So what I'm trying to share is that the domain-specific software architectures are a solution, and these are simply reference architectures that have been created. The last thing I would like to share is that the Mosa effort should align with any activities that are going on within the CCSDS and OMG. So the Spacecraft Onboard Interfaces Working Group and the activities going on within the OMG, so that there can be a lot of cross-pollination between the various standards bodies and very interoperable reference architectures. And I think that's what I want to share. Actually, if you can go to the last slide, the very last one. Yes, so these are some of the standards that govern space systems. You have NASA specifications, DO 178, NASA NPR 7150, things like that. The qualification exercise for 10 million lines of code or even 1 million lines of code is a non-trivial effort. So we need to think about these sorts of things as we develop domain-specific software architectures, reference architectures, and frameworks. And those are my comments.
Thank you very much. And last but not least, we will have Chad Thrasher, Systems Interoperability Lead, NASA's Artemis Campaign Development Division. Go ahead.
Thank you, APL and this consortium for having us here today. I think I speak for all the panel members on that. So I prepared my comments based on planning on speaking last. I'm going to try and pull a little bit of this together by talking about the Artemis missions after Artemis 3. So as that Artemis campaign returns to the moon and we start landing more robotics on the moon, robotics which are both teleoperated and autonomous, right? They're going to be delivered by the commercial landers. We've all heard clips talked about and possibly other commercial means. Those landers are going to be initially have the primary goals of scientific missions and mapping for future crewed missions. That's what they're going to be focused on. Maybe even testing some new equipment or testing new applications. But when crews start landing on the moon's surface, they're only going to be there for maybe 2 weeks at a time, with crewed missions being a year apart. So that means that all work on the lunar surface will be done by robotics for a majority of the time. That means with a crew there for 2 weeks out of the year, there's 50 weeks for robotics to do something on the lunar surface. Now, you got to take into account darkness, right? But we should be good stewards, and we should get the most work out of whatever we land on the lunar surface. And we should also minimize the waste, because the waste equivocates to dollars that we don't have to spend. So we need to generate a modular open system architecture framework for the lunar rovers that permits rover developers, NASA's, international partners, and other potential users to reuse the chassis, make repairs easier, and most importantly, provide the ability to add different scientific instruments or tools or upgraded capabilities without sending the entire system back to the lunar surface. That will lower cost, and it will make a long-term sustainability. Once a lunar Mosa compliant rover or robotic system is delivered to the surface, the modularity of the design allows a host of benefits that we've already talked about here today. But the biggest benefit is just having to deliver the end effectors or the tools that you need for the specific mission. My vision, one that I believe most of you share, is that industry, academia will collaborate with NASA to jointly develop a lunar Mosa standard, which may initially be based upon the Victory specification by the Army, not the Victory project.
1 minute.
That DoD uses but has tailored for lunar environments, vacuum, lunar dust, long periods of darkness, and long periods without maintenance. I would hope this new lunar standard, this Mosa standard, complies with existing international interoperability space standards, which are applicable, such as power, comm, avionics, and software. The ability of these systems to interact with other Artemis sisters like HABS, LTV, and future systems will be greatly determined by the extent that they comply with these international standards. As we have seen today in earlier presentations, the use of robotics may begin with small rovers that collect scientific data or map surfaces, but eventually they will become and evolve to bigger systems that move Earth and manufacture using in situ materials, or help pre-position supplies for an Artemis base. As the need for larger, heavier equipment develops and our ability to deliver that equipment improves, we need to continue to update this lunar Mosa standard to reflect the increasing size and capabilities of these systems. The initial systems, we need to have several of them that build upon each other. Not every system will work as designed. Some will exceed our expectations, but we need to learn from both. And this means that not only does the specification need to be open source and openly available, but also the lessons learned needs to be publicly available. So perhaps one day there will be a robotics bay on the surface of the moon that stores modules to do different jobs that are made by different organizations. And there will be robots that will select those modules and assemble them for a specific mission. And that mission could be supporting the long-term lunar base, testing a new technology, or supporting some scientific theory or experiment. It could happen. It should happen, and we need to take the first steps. Thank you.
That was excellent. That was also a perfect lead-in to my first question. So I'm just going to jump us right into the Q&A. Just checking. And ask. So Mark, who gave the first presentation to introduce Mosa, mentioned consensus-based standards. And Chad, you just proposed the Lunar Mosa standard. So what does that look like? Should there be a standards body to coordinate standards for the moon? And who or how should the lead be taken on that? Should it be industry? Should it be government? We can all probably point to examples of standards efforts that are dominated by one category of actor or another. So I'm curious, from a variety of the panelists, what is your sort of reference archetype for how an initiative like this could be pursued?
I can take the first stab at that, I think. I really think the best way to approach this is to find, for someone that's in charge, and right now, effectively the biggest player in the room and the biggest funder is NASA, right? So if NASA's going to put investment into something, we would say, hey, we would like it to comply with this. This mirrors, Mark, like what you said, what PM Force Projection had done, whereas they went to industry and they said, we want to do this robotics interoperability profile. Tell us what needs to be in it. Industry, we're not going to write it. Industry, go and write this for us and tell us what it looks like. And then they came back, developed it, and then PM Force Projection adopted it. And I think that, to me, I mean, maybe because I'm a hammer, everything looks like a nail. But that I think seems to be maybe the best approach to mirror that here, where NASA says, hey, industry or LSIC, because it's a consortium that developed it for DoD too, work with your partners, work with industry, to tell us what should be in the first versions, and then from there develop that into subsequent versions over time. But adopt this, make sure the subsequent versions are legacy compatible, and work from there. That's kind of how it's working up here anyhow. But welcome any other thoughts?
If I could add, hopefully I'm not stomping on anybody with latency, but yeah, what we did is we started with an industry day, probably like 2010, something like that. And we kind of had an initial outline of some of the standards we knew about. And we said, over the next 6 months, we intend to release version 0 of this interoperability profile. We think it might be partially based on JAWS, but we're not totally sure. And so we said we're going to break into 5 interface control working groups, basically, 1 for payloads, 1 for radio communications, 1 for basically overarching, and 1 for controllers. And we formed like mini working groups within each of those 5 whippets that were composed of both government people and industry. We had about 100 industry participants in that first kickoff. And so we kind of stormed and normed and got to where we thought we needed to be, like, I guess nowadays you might call it a minimum viable product. And we put that out as version 0. And then we continually ask for feedback from industry. And then once we go to like apply it to a particular program of record and put it in a contract, we basically say you must comply with these interfaces. However, we have another clause that says if that causes a problem for you from a systems engineering perspective or for another reason, you can recommend back to us an alternative interface for government approval, basically. And we'll take that under consideration and potentially adopt that alternative into the IOP in the future version when V1 or V2 or whatnot comes out. Over.
Well, thank you. Any other comments, or I'll jump to the next question?
I'll make a quick comment. So I do believe industry and academia that have been working on this already for the Army and other military systems probably should kind of take the lead, but NASA should guide them on what environments and the other systems are planning on deploying with the international interoperability systems that have already been agreed to through the Artemis Accords. So that should kind of set the larger boundaries, and then within those boundaries, to be able to interoperable with other systems like a habitat, then develop the standard based on previous applications.
Thanks. I am going to switch gears a little bit and say, how do we think that the possibility of a single dominant private actor, hypothetically, should influence our thinking about standards? Does it mean that we should let them influence the standards if they're going to be the ones that are basically deploying the platform? Should we avoid them taking the lead on standards? Is it a reason not to need standards?
I could answer this, or maybe Mark, I'm wondering what your thoughts are is with expedited leader follower, where it started and where it is now, or I don't know.
Yeah, I guess for the DoD, I guess maybe we have the advantage of the size of the market that we interact with is relatively small. And so I would say there's maybe 4 to 5 companies that are really like definitely competing with each other in this market. But so I guess how it played out for us at least is we said we're doing this IOP. We kind of continued to tell that story for a while. A couple of the companies really embraced that and said, we're doing our internal R&D to conform with the with the IOP, and therefore we've shown the ability to integrate these different payloads from these other companies, and it helped us. And then when the other companies saw that those companies that did that, then the other companies started doing it to become more competitive, and it kind of led to a de facto standard, I guess. Depending on what market you're in, that can be easier or harder. So that's part of it. It's really a good question. And I mean, in some cases, when one company's technology wins, maybe that's a good thing because it becomes a de facto standard anyway. Hopefully you would find ways to avoid the actual interfaces being proprietary. And find ways to separate their intellectual property that they really differentiate themselves with just the interface. And I think Amalaye has his hand up.
Yeah, I will say that the landscape has changed over the past 22 years. So in the late 90s, early 2000s, the dominant player was NASA, and you also had ESA as well. And NASA defined space standards, and they also qualified them. Shortly after that, the OMG became involved in space standards through the Space Domain Task Force. I was part of the team that defined the XTCE specification. And one of the interesting things to see after many years is that the industry adopted XTCE. And so XTCE is now all over the place. It's in wide use, and it's a specification that's widely used. XTCE is a telemetry and command database specification. So one of the things that I think is different is now you have different players in the realm. So you have commercial space, in addition to governmental entities, such as NASA or European Space Agency entities. And the thing that we have to be careful about is having disparate standards that pull the industry in different directions. So one aspect of this is that the OMG, whatever the opinions might be of the OMG, is an industry-driven group. And so they have a robotics domain task force. They have a space domain task force that are doing their thing. And those groups may not be talking with Mosa groups, or they may not be speaking with CCSDS. And so what is helpful is trying to get the players in the same room to have a conversation so that we don't have an industry that's pulled in different directions. And I think what we have now is we have several significant players in the landscape. And these players can drive the direction of what is a space data system. Then there's also the qualification of software, which is something I'm very concerned about.
Thank you. If you have a brief comment, and then maybe we'll switch to the next question, just to keep us rolling.
Just from a programmatic and economic perspective, the more suppliers you have, the better cost effectiveness you can get out of your dollar. So if we have a non-proprietary interface, then the modules themselves could be proprietary. And I think that way you could have the most people participating, not only from industry, but also academia in making the modules. And that way you wouldn't have a proprietary interface that you're reliant upon one particular vendor for.
Yeah, absolutely. I think that's a great point. So clearly, folks on the panel are inclined towards thinking that we will need standards in the lunar community. Matt kicked us off, and of course, Chad, you just made some suggestions in your talk as well. But what specific standards do all of you think that we need in the next 5 to 10 years? What is the first, if you were to choose 2 or 3 areas, what would they be? Meera, maybe.
Well, given that I work in robotics, I have some strong feelings about robotics. Really excited to see the work that is being done on space ROS for that reason, because we use ROS all the time in a number of different applications, ranging from different kinds of COTS robots to custom robots, and having ROS as something that we can use on all of those systems. It talks to the right cameras, it talks to our navigation software. Having that be able to tile those pieces together really makes our lives here on Earth much better in the robotics space. So I'm really looking forward to seeing ROS be used more in space.
And as far as, if we're talking domains, like I said and showed in my slides, I think power is one of the top priorities. I think it's easy enough to do, at least to get a V0 out there. Maybe comms, maybe navigation, same thing. And then I spent almost 20 years working for robotics, so guess what I'm going to say? Robotics. It just makes sense. And like I said in my slide, it's going to be, if you ask me, it's going to be the most robotics-dependent campaign undertaken by humanity. So let's do it.
Any other takers for that one, or is it just?
I guess I'll add a couple of thoughts. Yeah, I mean, obviously I'm not from your industry, but there's some Earth-based standards that you may want to take a look at reusing, just kind of no-brainer things like ISO containers and shipping containers, and like some of the Department of Transportation vehicle-to-vehicle, vehicle-to-infrastructure kind of standards. If you're looking to make it a smart moon, I guess. And then the question with some of those existing standards will be, did we get them right the first time on Earth? And if not, then maybe we need a different standard. And that's why you have the advantage of the whole greenfield approach for what you're doing. And then also talking again about ROS and everything, we use ROS also for military, and we specifically have a project called ROS Military that actually SWIRI is involved in. And long story, but we've got a website called rosmilitary.org, which is for software reuse, but we've got this thing called the Robotic Technology Kernel, RTK, which is basically a series of software. You could call it microservices for autonomous mobility applications that you may be able to utilize to some extent. But with Amalaye's concerns about software qualifications and things like that, we have those concerns also with autonomous vehicle safety and things like that. And so we're developing this thing called a software foundry, where we're trying to get to that whole agile DevSecOps thing where you frequently do your software deployments. And we're in the process of converting that RTK software from ROS 1 to ROS 2, which is more the publish subscribe DDS, distributed data service model, which should enable a little bit more of those more modularized within the autonomous software in the future. But that's all I wanted to add. Thanks.
Thanks for that. And I'll just, oh, sorry, who's,
I have one as well.
okay, great.
I'm in robotics, but my answer is not robotics. My answer is disruption tolerant networking. How do you do pub sub and scale pub sub over millions of miles? I've done it before. 25 million miles, publish and subscribe. And the answer is disruption tolerant networking. Those specifications are open, it's open source, it does work. And I think that that's the enabling technology to scale, publish and subscribe over hundreds of thousands of nodes, over millions of miles. I think that that's the only way right now at the present to do that.
Yeah, that's a great one. And I feel compelled to add one that I haven't heard here, but I've heard from a lot of folks in the community, which is payload interfaces, mounting interfaces, standard geometries, but also power, comms, et cetera, has been talked about a lot in the CLIPS ecosystem since they aren't standardized yet.
Yeah,
Okay,
if I could add a couple just on that payload physical interfaces thing.
Mark,
just-
if you can
just-
make it brief, just because we've got to wrap up and switch to our closing speaker, then that would be great. And we'll do maybe a quick lightning round.
Okay.
Great.
I just wanted to add that for our IOP, we have two of those things that we use as a standard. One is called Picatinny Rail, which is basically the same connectors they use on guns for attaching different types of payloads. And then the other is called Optical Bench. It's basically just a pattern of holes for standardizing that. That's all.
That's awesome. Okay, if we have, we're going to try and do this in 2 minutes, but since today's theme is envisioned futures, I think, again, Chad modeled this very well. So riffing off of that, the last question is, in your wildest standards dreams, what might standards, the existence of standards, make possible? If we succeeded, what kinds of applications, activities, or services would standards enable? And anybody wants to take that, maybe besides Chad, since you sort of cheated.
I guess I'll take a quick stab. I mean, to me, the previous speaker mentioned using different payloads on reusable equipment, and basically that leads to the question of highly interactive, basically smart systems that connect with each other. And somebody else mentioned the robots themselves selecting and configuring the payloads on their own to optimize the work that they're doing when the humans aren't around. And I really think modular interfaces and standards can really help enable really smart system level behavior. Over.
Yes, the good idea, Ferry. What the vision could look like. In my wildest dreams, I would love to have, assuming we have this open architecture, this that allows interconnected modules like Legos, right? And then each of those, picture each of those Lego blocks: comms, radio, chassis, wheels, batteries, electronic circuit boards, software, autonomy, perception sensors. Every single one of those, they're all separate. And you can open source development of each and every one of those little Lego modules to the point where you can have crowdsourcing, and you can have a 8th grade student developing software that's going to go to the moon someday, and a web developer for Oracle or something saying, you know what, I like software. Another person working to develop the circuit board designs and do thermal analysis, and someone that loves to do QA to take time in their evening time to just go in and study this component. And all of this being open to the open communities all around the world. And then whoever wants to fly something, take the parts they need, assemble it, qualify it, build it, and fly it.
Awesome. Any other takers?
I'll take this one too. It's kind of similar to yours. The idea of having a rover that you could maybe put an arm on, or maybe you need 2 arms for something, and you can swap out the end effector. You can swap out the camera depending on the mission. You can upload new code to it while it's on the lunar surface, so then it can perform a different function or a new function, or you can send a new end effector and send some code up as well. The idea of being able to do that really opens up a lot of doors for us.
So just real quickly to add on to what Matt was saying, software management at the module level and software or system management at the rover level, and then some overall level of management to decide how to allocate each of the modules so you're getting the most use out of which modules you supply. I think there's 3 levels of software you have to develop.
And my thoughts are, as the cost of getting to orbit goes down and you have more qualified modular open systems, that intersection when the cost of getting to orbit is low enough and you have lots and lots of modular building blocks, as was shared earlier, that's going to be a really interesting time just to see the types of systems and things that people deploy in space.
Absolutely. Thank you. Thanks all. Gonna switch it over real quick for some closing comments from Sandy.
So to close on today's panel, I want to bring in another really important perspective, and that's the perspective of an operator. So Dr. Magnus, who is an astronaut and who has been to space several times and has been on the International Space Station, has some wonderful stories about her time up there, and we really want to hear her perspective.
Anyway, yeah, thank you. This has been a great discussion, a very, very important discussion, and one that's really needed. I'd like to sort of take it orthogonal for a minute, because this has been very technology focused, as is understandable given the community. But I would invite you to look at this from an operations viewpoint, and not just from the human use, but also George Sowers mentioned earlier from a maintainability and a logistics viewpoint. We're used to designing systems from a technology lens, and sometimes the interoperability and the use gets a little complex. Like, for example, on Space Station, we've got 2 different fundamental voltage delivery distribution systems. We've got a 12-volt system in the Russian segment and a 120-volt system in the US segment. So every time I wanted to plug in a piece of equipment, I had to find what we affectionately call a brick. We had white bricks, green bricks, and blue bricks, but each one about the size of a toaster, and each one's purpose was to transform between one voltage to another, depending upon what we were trying to plug in. Because we also had legacy shuttle equipment that was up there that worked off of a 8 or a 10 volt, I forget which. And each one of these bricks had a different physical cord keying. And so not only do we have to keep track of the bricks and where they were and how many there were and what we could plug into them, but we had to keep track of the corresponding cords. So that's clearly not a good system that interoperates. And so as you're thinking about interoperability, I would also suggest that you consider this through the lens of the operator. And just from the human viewpoint, I didn't hear anything about gas ports like O2 ports or N2 ports. And so if you think about the suits that we're going to have, there's probably not going to be one person or company that delivers suits. There might be all kinds of suits, and that those suits will have to be recharged. And the robotics will be creating these gases, and so you need to think about the connectivity. So when you're thinking about interoperability, look across the human and robotic system, find those common areas, and make sure that you definitely have a set of standard interfaces or standards for that type of the system. And then when you go just into your robotics world and you're worried about just the interoperability of the robotics, think about the maintenance. And it also means that you might have to optimize. Someone talked about optimizing from a systems engineering viewpoint and trying to develop your system, and you may have, maybe you'll have some exceptions if the systems engineering is difficult. I would argue that instead of looking at that through a systems engineering lens, and I'm an engineer saying that, and I can't believe it, but look at it through a logistics and an operations lens. So maybe your systems are a little bit suboptimal from an engineering viewpoint, but they're optimal from a logistics and maintainability viewpoint, right? And so it's a little bit of a different way of looking at it. And then I have a couple more points. Number one, when you think about standards, the first thing to think about is standards are the solution to a problem. So what is the problem that you're trying to solve? So for example, if we're trying to solve the problem that, any system on the moon, human or robotic, that needs to interface with an oxygen port, that has to happen. That's the problem you're trying to solve, and the solution is a standard interface, right? So don't just jump to standards for standard's sake. Think about what is the problem that you're trying to solve. And that might help you figure out where you want to, put your your priority as you design these systems. And then finally on infrastructure. People throw the word infrastructure around a lot, and there's a lot of different definitions in their head as they do that. You know, NASA has stated very clearly today, and they continue to state very clearly, that they are going to the moon in order to learn what they need to do to go to Mars. That's their mission. They're going to do that, and they want to do that in the context of allowing industry to come behind them in a much more accelerated way than we've done before in low Earth orbit. They want to bake it in from the beginning to build an infrastructure, if you will, or a set of systems that they can leave behind as NASA move to Mars for industry to be successful. So for this community, I think it's really important that you feed to Chad. And Chad, I would love to see where you are in your interoperability viewpoint and what you're deciding should be. But if this community should be feeding into NASA what you think the infrastructure is that you want them to leave behind for you to be successful when they are gone. Right? And then that will also drive your top level series of conversations about interoperability and standards from the industry viewpoint, which may or may not match 100% what NASA thinks needs to be interoperable, because they are also dealing with international communities. You know, I mean, you think about just traveling around the world right now, how many take, 7 different plugs with you every time you leave the country, right? And so they've got another dimension of interoperability that's even beyond what you guys are talking about. But anyway, I just wanted to throw some of those things out for you to think about from, again, the operator viewpoint, including the maintenance and logistics, because it really is going to require a little bit of a different mindset than our typical systems engineering, where you're trying to decompose your requirements, optimize at the subsystem level, put it all together and see what you have, right? That's not, usually we bring the operators in last, and I don't think we can afford to do that in this expansion that we're going beyond all of the wonderful resources that we have here on Earth. So anyway, just a few food for thought. Thank you for letting me jump into the panel, and I'll have a seat now.
Yeah. Thank you very much, Dr. Magnus. And I want to thank all of our panelists today, Mark Mazzara, Mary Day Towler, Matt DeMinico, Amalaye Oyake, and Chad Thrasher. And I really want to thank Jessy Schingler for helping me moderate this. And that is the end of the Mosa panel. Thank you.